Good morning, good afternoon, good evening, and welcome to this webinar by World Nuclear Association. Uh, World Nuclear Association, as you know, is an international organization that represents the global nuclear industry. I am Sama Bilbao León. I am the Director General of World Nuclear Association. And today we are thrilled to have this special webinar where we are going to explore the essential role that that nuclear energy can have in decarbonizing sectors beyond electricity. So you know that nuclear has a very important role to produce low carbon electricity. It has this role today and has had it for the last 5 decades. So that is well known, and even though it's not always recognized or valued. And of course, you know that nuclear energy is the largest source of zero carbon electricity in developed countries. But what is less well known is that nuclear energy is the only zero carbon energy source that can produce electricity and heat. And we truly think that this is huge because it opens very exciting opportunities to decarbonize hard to abate sectors such as industry, heavy transport, and many other sectors beyond electricity. Unfortunately, this very important potential is currently not very well considered, or actually not considered at all in any of the mainstream scenarios proposed to achieve net zero by 2050. The IPCC has developed over 90 scenarios, and just last week, the International Energy Agency released a very important report, the Net Zero by 2050 report, that provides a how-to guide for global decision makers to achieve the 1.5-degree goal. So this report has been labeled as one of the most technically feasible, cost-effective, and socially acceptable paths to net zero. But even so, the IEA gives this plan about a 50% chance to actually achieve this 1.5 degrees goal. And while most of these scenarios include a contribution of nuclear energy for the generation of electricity, and in this case, we are doubling the contribution of nuclear capacity for electricity generation, none of these scenarios actually include any role whatsoever for the nuclear heat. So in our opinion, this is a great opportunity that is lost because given the urgency and the enormity of the climate change challenge that we are facing, it is very regrettable that a tool such as zero carbon nuclear heat that is readily available right now is not being used to achieve this zero carbon. So, you know, this is part of the reason that we started today with this webinar. We really want to highlight 2 studies that actually evaluate the very important role that nuclear can play beyond the decarbonization of electricity systems. So one of them is a recent study made by EnviroEconomics and Navius Research, which is titled Emission and Economic Implications for Canada, using small modular reactors in the heavy industry. And the second one by TerraPraxis is titled Missing Links to a Livable Climate, how hydrogen-enabled synthetic fuels can help deliver the Paris goals. And of course, to present these 2 studies, I am super lucky to have today with me a group of experts that are going to present in depth these 2 studies. So let me very briefly introduce them, all of them. And as I call your name, please turn on your camera so everybody can see you. So the first of our speakers will be John Gorman, who is currently the president and CEO of the Canadian Nuclear Association. So John brings very, very unusual skills to the nuclear community as past president and CEO of the Canadian Solar Industries Association, and also as director of the board of the Energy Council of Canada. So really, he was the founder of the Canadian Council of Renewable Energy. And I think that his experience has been instrumental to make sure that nuclear energy can secure this leading role in the energy transition for Canada, of course. So welcome, John. It's a pleasure to have you. Together with John, we have Erik Ingersoll, who is one of the co-founders and managing directors from TerraPraxis. Erik is a strategic advisor and entrepreneur with a lot of experience in the commercialization of new energy resources. So he's been working in a lot of projects with policy in experience in renewables, energy storage, oil and gas, and of course, nuclear. And of course, he's very focused on advanced nuclear technologies. And then I would also like to introduce Dave Sawyer, who is an environmental economist with over 25 years of national and international experience in economics of climate policy and energy futures. So, and finally, I know that all of you were waiting to see Kirsty Gogan, which of course is a co-founder and managing partner also of TerraPraxis. Unfortunately, at the last minute, Kirsty will not be able to join us. So no pressure, Erik, but you have the entire weight of your presentation on your hands. So this is the very stellar lineup that we have for today. So I think that without further ado, I think I am going to invite John and Dave to start with your brief presentation of the results of the study that was done by EnviroEconomics and Navius Research. So the floor is yours.
Thank you. Thank you very much, Sama. I'm delighted to be here this morning and to be talking about uses for nuclear outside of electricity production. I think, given the genesis of nuclear power, we've always had a very electricity-centric mindset. And of course, especially with the introduction of advanced nuclear or small modular reactors, as we call them in Canada, we have the prospect now for very high temperature heat, clean heat, 24/7, very flexible, which is producing and scalable, which is producing all sorts of interesting opportunities for us as a world when it comes to interesting things like using that heat to decarbonize heavy industry or produce hydrogen, desalinate water, etc. So thank you for having me. And Sama, may I just say thank you for this very proactive leadership that you are showing with the World Nuclear Association in terms of helping to bring this closer coordination and collaboration between the world's nuclear associations and nuclear-related and environmental-related organizations. Now, of all times, we need that level of collaboration and coordination, and your leadership is very much appreciated. So what I'd like to propose here is that we go through a slide deck quickly between Dave Sawyer and myself. I'm going to set some context for those listeners who aren't very familiar with the Canadian nuclear scene, and then I'm going to hand it over to Dave to talk about the findings of our study, as he was the lead environmental economist on it for us, and in fact is Canada's leading environmental economist, whose work is fueling the federal government and a number of our provincial governments' work on carbon pricing and environmental policy. I'm really pleased to be working in partnership with him and his partners. So just quickly, in the Canadian context, nuclear provides about 15% of our electricity. Our most populous province and certainly the largest economic region in Canada is Ontario, and for over 60 years, we've been providing about 2/3 of Ontario's electricity here. And we're also producing about 1/3 of New Brunswick's carbon-free electricity. We have the full spectrum of a nuclear ecosystem here, everything from the creation of uranium to being a tier 1 nuclear operator. We also are a world leader in the creation of isotopes, not just cobalt-60, but a number of other isotopes, which I'll speak to in a moment. We're finding very innovative ways to produce these not only in sort of laboratory settings with laboratory reactors, but also with our power reactors themselves. Some interesting work going on there. In the Canadian context, the nuclear industry is quite large as well. We employ 76,000 people, $17.3 billion contribution per year to our gross domestic product. So let me just give a little bit of a perspective on where I think Canada sits in the world as a nuclear power operator and a tier 1 nuclear nation. I think Canada is doing almost everything right, if I could say so. You know, we have a long history of safe nuclear generation and operation. We've got a world-class regulator. We are refurbishing more than half of our existing units right now. In fact, it's Canada's largest infrastructure project, which is why we're employing so many people and why we have such a healthy nuclear ecosystem here in Canada. And it's on this foundation of this refurbishment and our long and proud history in nuclear that we're doing some very innovative things in relation to small modular reactors and advanced nuclear, in the field of nuclear medicine, in particular with isotopes, certainly with the work that we're doing now in concert with other parts of the energy sectors. We have a very strong coordinated effort going on right now to create a hydrogen economy, which is going to we hope rely quite heavily on existing and new nuclear potential. A number of our provinces have committed to that. Our CANDU technologies are in a number of countries around the world, and we're currently exploring new opportunities for the refurbishment and new build of CANDU reactors. So we have, I think, all of the elements here from refurbishment to innovation that are important. And as it is particularly relevant to this discussion today, I'll say that our leadership, or our first mover position in the free world anyway, on small modular reactors is quite significant. You know, we have an incredible collaboration going on between the federal government, 4 provincial governments, 4 major utilities in Canada, our regulator, and between these organizations, we have been able to put together a very comprehensive plan for the development and deployment of small modular reactors. As a result, we've got 12 different technologies going through the review and licensing process right now in front of our regulator. And one of those technologies is into the licensing process now. So we're looking at timelines of sort of 2026 for very small modular reactors coming online, and we've got a commitment for 2028 for a larger small modular reactor coming online by one of our major utilities. I think Canada views it as important to be a leader in small modular reactors because we have a number of sectors that can use it for decarbonizing and for providing more than just electricity, but electricity and heat. So in the Canadian context, it's important to remember that we're not going to get our carbon savings as we work towards a net zero future by cleaning up our electricity system. Our electricity grid nationally is already 82% non-emitting, which means that we have to look to other sectors of our economy for decarbonization. We're very dependent on natural resources here and extraction and heavy industry for our economy. And so it's in these places that we have to look for GHG reductions. And when you consider that this carbon pricing regime that we've adopted as a nation covers about 80% of what happens in our economy from an energy perspective, about half of that, so about half of the emissions that we're trying to deal with come from heavy industry. And so it's for that reason that we have been working with Dave Sawyer and EnviroEconomics and Navius to understand what small modular reactors can do in our heavy industry sector to help deliver on some of those very hard to decarbonize areas. The last thing I'll say about our small modular reactor approach here is that we've divided it into 3 streams. Stream 1, which is on-grid applications for electricity. Stream 2 and Stream 3 deal with either next generation nuclear reactors or the very small reactors. So for us, especially given the fact that right now we have quite a clean electricity grid and we need to look at the applications of nuclear in these other sectors, we approached environmental economics and EnviroEconomics and Navius Research to do a study for us to look specifically at the applications of introducing small modular reactors into heavy industry and what impact that could have. And so I'm going to ask Dave Sawyer to bring us through the highlights of what that study found.
A lot of work in Canada on net zero sort of pathways out to 2050. So taking Canada's emissions from about 730 megatons currently down to a net level of under 100 megatons of emissions. So year over year declines in emissions in the order of 14% off of current levels. To give you an idea, Canada's current carbon pricing regime at $50 a ton, plus a whole bunch of allied programs at the provincial and federal level, is really delivering about 1 to 1.5% year-over-year reductions in emissions. The new $170 carbon price the federal government has floated to 2030, sort of climbing from $50 in 2022 Canadian to 170. That gets us on a pathway of about 3% emission reductions year over year. And we really need to get down to sort of year over year 14% reductions to hit a net zero pathway, in the life of one industrial boiler or one oil sands facility, one petrochemical facility. So massive transformation. So we have a modeling framework where we do a lot of analysis for the federal, some for the federal government, and a lot for the provinces, looking at various regulatory scenarios. It's an economy-wide economic model with sort of an end-use technology choice model. And basically what it allows us to do is to look at these net zero pathways and introduce new scenarios into the analysis. So for this study, we added SMRs into the analysis, 10 different scenarios, assuming different technical readiness levels and different cost assumptions, given uncertainty. And we added these into various industrial end uses where there's a need for high grade heat and some power. So we didn't look at the electricity sector at all. And then we basically tumbled the model and allowed the model to solve, on what are the sort of cost effective pathways by the various industries to hit this overall net zero pathway. And what we found kind of surprising is that the carbon cost, whether it's a carbon price or a regulatory shadow cost, was lower across most of the SMR scenarios. And it resulted basically, and we're trying to hit the same emission reduction. And these results, to think about these results that we're showing you, what happened is you're basically shuffling out high cost abatement opportunities in some sectors like hydrogen, renewable natural gas. The SMRs come along, outcompete those. That then frees up that stock of those sort of emission reduction technologies to be used elsewhere, which makes their life a little easier. So you basically have this integrated approach where you're shuffling abatement opportunities around. And we found across these range of scenarios that we were getting basically cheaper costs for the same level of emission reductions. And it was quite a surprising scenario for us. And I should say the cost assumptions we use, the federal government has an SMR readiness roadmap. So we use those sort of those costs. And as I said, we did a range of uncertainty testing, and we found these results to be pretty resilient across the range of results. And yeah, so what does this look like? So 14 megatons reduction annually coming out of the industrial sector. So fairly large levels of reductions. As John said, about 40% of our national emissions are currently covered by, coming from large industrial emitters, and cement, steel, oil sands, petrochemicals, fertilizer, you name it. Anybody emitting more than probably 25,000 tons of a year, so quite large facilities. And basically we found, the equivalent of sort of 3 million cars off the road was coming out of the SMRs that were deployed in the average scenario. So this climbed a high as 28 megatons a year, and a low side was about 5 megatons a year. And those are the extremes, as it were. So John, yeah, you can move on to the next one. And then, yeah, cumulatively, this is a very, when you think about carbon budgets and net zero, carbon budgets really matter. And this size of this reduction is quite large, given what Canada has to do. I should also say that we didn't allow the SMRs to compete until after 2030. And we really don't see SMRs come on being really strong until after 2035 and in the 2040 range. And in the context of the IEA scenarios that just came out, in Canada, we've been doing a lot of net zero work with a group called Climate Choices. And we ran 120 scenarios there. And we thought about these abatement technologies two ways. One are the safe bets. So you can think about energy efficiency, renewable power and electricity. A lot of these sort of technologies we see today that are competing, that you just basically, they deepen across these scenarios and their emission reductions. But then we have all these wild cards that there are multiple competing pathways for emission reductions, like hydrogen, like electrification, in some end uses, like electrification, like SMRs. And it's really the wild cards in the 2035 timeframe that we're really uncertain about. And we know that we have to do something with those emissions. They're hard to abate, and these wildcard technologies come on later in the future. There's competing technology pathways. There's uncertainty around the technical and economic costs of the emission reductions. But what we found is that in Canada's case, these wildcard reductions are really important to get to net zero. We can only get so far. We get about half our emission reductions from sort of these safe bets, but it's these wildcards that really come in the future. And that's a whole suite of technologies. And picking winners now, single winners, means you may be in a dead end pathway later on. So the policy advice is you have to be a little more broad in your view of these wildcards. So I thought that was an important piece of context. So John, thanks. And so in the industrial sector loved the SMRs at the costs we put in, about $80 to $90 Canadian a kilowatt hour was the sort of the cost we put into the model with some variable costs. And the SMRs didn't capture all the emission reductions, but they captured a significant portion. So we still have a lot of carbon capture and utilization in the system, but we also, as I said, we have a lot of these wildcard technologies like the hydrogen pathway, the renewable natural gas pathway, some applications of CCS in unconcentrated streams of industrial emissions. The SMRs absolutely took off. So this is a surprising finding for us, as I said. John, next slide, please. And so this was the bigger surprise. We rarely see in scenarios a reduction in costs, a reduction in sort of balance sheet costs. So sort of at the facility level, if you can get the technology working, your compliance costs are lower for the net zero pathway. And then on aggregate, nationally, we saw GDP was the slowing of GDP on the net zero pathway was significantly lower. So this, and the carbon prices we're talking about here climbed from $170, right? And then the question is, where's the backstop technology and where do SMRs fit in? But we do have a whole bunch of direct air capture in the model. And in the end, SMRs came on really strong. And so it was an interesting finding. And then I'll just close off back to this wildcards notion. There's a reason we need to think about all these technologies and sort of nurture them and not lock ourselves into certain technology choices that may be dead ends. So that's it.
Thank you very much, John and Dave, for this presentation. So, now I think I'm going to invite Eric to present to us, to give a brief presentation of this report that TerraPraxis has recently released. So up to you now, Eric.
Well, thank you, Sama. I echo all John's comments about the role that you guys are playing and the way that you're helping the World Nuclear Association kind of step up to a key leadership position in what's going to be a very difficult 29 years here as we try to get to 2050 and zero emissions. This is really I'm going to go quite quickly because there's a lot of content here and we don't have much time, but you're all welcome to find our report on our websites, and I'm also happy to answer any questions that come up. So this is a graph that we see all the time, this pathways to net zero. But we don't always see what the to-do list is that's associated with this graph. And so we've put that on this chart here, which means that we have to repower all the coal plants or shut them down. We have to convert all liquid fuel to carbon neutral fuels or stop using the liquid fuels. We have to replace all natural gas uses with hydrogen or ammonia. We have to do this while we're dramatically increasing the amount of energy use in the developing world, and while we're electrifying everything as fast as possible. And it's also important to point out that sort of halfway through this graph, the pathways are below the zero line. So that means that a large amount of energy needs to be invested in removing carbon dioxide from the atmosphere, in addition to all the other stuff I've mentioned. And what we see today is that the stated commitments that people have made, I think the flyer for the event mentioned that there's only, we're sort of getting about 1% of the reductions that we need. The stated policy scenario for the IEA still shows that we're about 70 to 80% fossil fueled on a total global energy system basis. So that's a very far cry from what we need to do in the previous graph. So our organization, TerraPraxis, has really said one approach to decarbonization is behavior change, changing all the end uses to electrification. You know, there's a very comprehensive and well thought out and you know, thermodynamically efficient approach to using less energy to accomplish the same things that we do that we do today. The problem is there are a lot of very complicated network effects. There's a huge sort of social adoption risk. There are a lot of other factors that that don't invalidate this path, but make it highly risky to depend on this path as the only path that we have for decarbonization. And if you look at most of the adoption curves that are required for all these different things, you can see that we're far behind what we need to be doing. And we haven't even entered the kind of high levels of deployment that are needed for this. So we have this idea for a complementary strategy, which we call the impossible burger strategy, which means that instead of decarbonizing, instead of transforming the end use and transforming people's way of doing things, you basically make them a vegetarian burger that they can buy where they buy burgers today. So you make them a plant-based burger that they can buy at Burger King. And the sort of, the way we think about this for fuels is that the idea would be to make synthetic carbon neutral fuels on the scale and at the cost that people are used to today to help decarbonize this 100 million barrels of oil per day habit that we have. And to do this, we need very, very, very cost-effective hydrogen. So this is not hydrogen to put in buses or hydrogen to put in special hydrogen airplanes that we don't have today. This is hydrogen as a feedstock for synthetic fuels manufacturing. And the diagonal lines on this chart show the cost of that fuel based on the cost of the hydrogen input. So in the vast majority of the cost of making synthetic fuels that contain hydrogen is the cost of making the hydrogen. So for ammonia, the red line, you can see that if you want your ammonia to cost on an energy basis something similar to what oil costs, you need to have ammonia, you need to have hydrogen being produced for around $1 a kilogram. If you're willing to have it be the same price as higher oil prices, you can go up to $1.50. For making synthetic hydrocarbons, which require more energy, and you have to reduce the CO2, you need an even lower production cost for the hydrogen, so below $1 to stay within the sort of cost competitive range. So we believe that if you can do this, if you can make fuels that are cost competitive and carbon neutral, we will have, the policymakers and consumers will have a much easier time decarbonizing and kind of forcing the rest of the system to adopt these things, which are cost neutral. So how can we do that? So our report explores two different models to achieve high volume production and to achieve very low cost facilities. And the first approach, they both involve kind of the manufacturing model being applied to nuclear energy. And the first one is bringing the factory to the facility. So the idea here is that you make a fully integrated manufacturing and deployment site. The two buildings at the upper left are where the reactors and reactor related equipment and the concrete related components are made. The left-hand lower black building is a precast facility. You can see reactors being deployed directly from those factories into the reactor farm that's being assembled from the precast components that are coming out of the factory. So imagine the entire production process with all the benefits of lean production techniques and high efficiency, manning and staffing and so forth. Imagine all of that applied to the entire process of manufacturing and delivering and installing. And then once those are operational, they're producing hydrogen, and that hydrogen is then being used in a synthetic fuels plant, which you see at the extreme lower right. This is basically the equivalent of a mid-size refinery. 12 of these would provide all the hydrogen that would be needed to substitute for the entire natural gas use of the UK. So this is a kind of a module in a comprehensive decarbonization strategy. The other approach is to bring the project, the production facility that's going to make the fuels, to the factory. And in this case, the factory is a high volume, high efficiency, high quality shipyard that's making hundreds of commercial ships today. And here you see the large FPSO, the floating production and storage platform, being assembled out of super modules in the front of the image. So this is really what we're doing here. The first one is we're sort of applying kind of modern factory and refinery thinking. Here we're applying the kind of these FPSOs for sitting on top of offshore gas wells are already made in relatively large quantities by the oil and gas industry today. So we're kind of taking a system, a production system and a supply chain that already exists and is already at scale, and we're just adding a new energy source to it, which is advanced SMRs. So here you see the 1.2 gigawatt. So it's got 4 SMRs in it, and it's been anchored off the coast of Singapore, let's say, and it's making fuel for ships, which are now burning ammonia. And you can see a bunker picking up the ammonia and to take it over to a ship and refuel the ship. 40% of the marine fuel that's put into ships in the world is put into ships by companies in Singapore. And then this is another version of this. This is a multi-product platform that's producing power and ammonia and fresh water. And it's kind of built on the same architecture, but it's to provide a combination of fuel, power, and water for a country in Africa. So what kind of cost reductions can we get from switching in this way, moving the project to the factory or moving the factory to the project? Well, in the West, we're familiar with the costs of first of a kind nuclear plants being built by EDF or being built by Westinghouse. And when we look at those costs, when we look at the kinds of things that are in those high costs, you see that many of those things are not costs that will occur when you build the next plant. So training your workforce, working with the regulator to get the design approved, et cetera, et cetera. There are a lot of costs which, if you're sensible, you shouldn't have to pay again. We call that that's sort of like second of a kind costs. When you are actually doing that and building a series of plants after your initial plant, and you design the program to achieve low costs, we call that the programmatic cost of building a plant. And what we show here with the light green cost savings and the dark green costs in the second bar, you see the programmatic costs that have been achieved in the past in multiple locations in the US, in France, in Japan, and so forth. We then have done very detailed analysis of which components you would need from a plant if you were building that plant in a shipyard, and what the components that would be supplied by the shipyard and what those would cost. So that gives us additional cost savings of building a light water reactor in a shipyard. That cuts the programmatic cost in half, from about $4,000 a kilowatt to $2,000 a kilowatt. Then if you're able to use an advanced reactor like a molten salt reactor, or a reactor that has kind of different power density, different requirements in terms of pressure vessels and so forth, and higher output because of the higher efficiency of the power cycle, you're able to achieve further simplification, further cost reduction, and increased output from the same sort of kit of parts. And that gives us what we call the advanced shipyard cost. Although that's a dramatic cost reduction and is much lower than anyone is generally thinking about what nuclear could cost, we believe, and we've done a study on this with the Electric Power Research Institute, we believe that there are further cost reductions that would occur from high volume manufacturing. So there's a real pathway towards achieving the kind of cost that would make very large scale production of hydrogen and synthetic fuels competitive with today's fossil fuels. I won't, there's a lot of information in this chart, but the key sort of thing to notice is that the blue shaded area at the bottom of the chart it corresponds to those threshold prices that I showed on the guardrails chart earlier for the cost of hydrogen needed for synthetic fuels production. And you can see that there are not a lot of options right now that can produce in there in that price range. We believe that reactors, large light water reactors being built in China today, achieve cost low enough that if combined with high temperature electrolysis, they would be able to produce hydrogen for $1.50 or less. And that the kinds of innovations that we're talking about for the gigafactory or for the shipyard models would create the sort of $1 type hydrogen cost that we need for broad scale deployment of these fuels. So there's a nice chapter in our report that talks about, well, how many of these things would you have to build in order to fully decarbonize by 2050? This is excerpted from that and shows the substitution of these clean fuels, these carbon neutral fuels, for our total fuel consumption, and shows the kind of elimination of the carbon component of those fuels. We also do a calculation based on the detailed cost studies that we did with EPRI, looking at if we were going to achieve the scenario I just described in the previous graph, how much investment would there need to be? So what is the total aggregate investment needed? And it turns out that if you take the fossil fuel industry's sort of expectations about how much fossil fuel they'll be delivering, which is actually similar to the stated policy scenario, and you look at what they would be investing to maintain that and expand that flow of fossil fuel, it's about between 24 and 25 trillion dollars to 2050. If you implemented the strategy with the production platforms and the gigafactories that we described, our estimate is that would only require about 17 trillion in investment. So less investment to clean up the entire fossil fuels sector than to continue producing the fuels. So this is something that large oil majors should probably pay attention to. And then we also did a calculation that if you tried to do that same amount of hydrogen production to enable those fuels with renewables, and you did that using renewables forecast prices for renewables after 2040, so taking very low numbers for the renewables, you would end up spending about $70 trillion. So there's clearly a low cost path here that, as Sama was pointing out, should be looked at very carefully by the people planning the energy transitions. So I'm not going to go through this. There's some great slides there's some great pictures in our deck. Basically, we looked at what would the land area needed to produce the hydrogen for several countries to substitute for their current oil consumption. What would that look like? And here you see the offshore wind farm. So that's a single offshore wind farm in the red outline. The single solar farm that would be needed in the UK, and the little green dot is the sort of space that all the gigafactories would take up. And we did the same calculation for Japan and for Korea. Obviously, these are not designed to be feasible because there would be sort of other people interested in that ocean area besides South Korea. So thank you very much. I look forward to your questions.
Thank you very much, Eric, for this presentation. So if I may, can I please have John and Dave to please also turn on your camera so we can all see each other as we start this round of questions. So we are starting to get some questions from our audience, but perhaps because I'm the moderator, I'm going to take the opportunity to ask maybe my first question. So I will start with John. I think that this is very specific to Canada because I think it's a very, very good example of a country where I think that you have a very fruitful dialogue and very good alignment, I would say, among government and the various different energy industries, wind, solar, nuclear, of course. So it also seems like you have done, the government in Canada has done a very good job, a lot of effort to really engage with all the relevant stakeholders, including, the indigenous communities, the people that are going to be affected by the phase down of the fossil fuel industry, etc. So within that entire context, how are small modular reactors perceived in Canada, and perhaps in this entire 2050 zero carbon net zero discussions, and perhaps specifically your report, what kind of feedback have you received from the overall Canadian stakeholders?
Thank you. Thanks for that question, Sama. Let me say, first of all, I think we've achieved a breakthrough with small modular reactors over the last 2 years in particular. There's a lot of work that went in before that, sort of foundational work where working with the federal government industry did the SMR action plan, which was very widely consulted and a real business plan for rolling out small modular reactors, etc. But from a stakeholder engagement point of view, the last 2 years in Canada had a really focused effort on engaging stakeholders, policymakers, think tanks, moderate environmental groups, renewable energy associations, etc., and industries to make a role for small modular reactors as clean energy that is required for a net zero future. And we've been successful in positioning and gaining acceptance for small modular reactors in that sense. Most notably, leading into Christmas here, the federal government, this federal government for the first time in its official documents and policies, programs, has acknowledged nuclear as a clean which is increasingly important, right, for all of the policies and funding dollars that are available have to be for that purpose, and needed for a net zero 2050 future. So that was a bold position for our federal government to take. And I feel now that we are in the mix of technologies that are being supported as we work towards a net zero future. One thing I will say though, Sama, is, you know, this journey, because you spoke about the sort of collaboration with renewables in Canada. It's been a journey. 2 years ago, the meetings that I would have with my counterparts at wind, solar, water power here in Canada, they were a bit tense. A lot of discussion that was needed to understand how nuclear could fit into the mix, how it actually supported the deployment of more variable sources of renewables here in Canada, and we've got examples of how that works. And you know, 2 years later, we meet regularly on a weekly basis. We put together joint op-eds, joint policy statements. We're working together on a broader clean electrification strategy for Canada that will try to encourage what we all know is a need for 2 to 3 times the amount of electricity generation we have in Canada. So it's been a very concerted effort, focused. It's taken patience and understanding on everybody's part, but there's a real recognition now, I think, among these stakeholders that small modular reactors are going to be required for a net zero future, and I think a growing appreciation by the other electricity sources that small modular reactors complement rather than compete with their technology. So we're pretty satisfied with that.
Yeah, no, I truly think you guys have been doing a very, very good job in Canada to achieve this consensus and this truly inclusive alignment. So this is definitely a model for many of us to try to imitate. So very good. I think that Eric wanted to ask a follow-up question to this. Is that true?
Yes, thanks, Sama. Yeah, I very much enjoyed the presentation of that sort of economics and economic benefits and the overall cost of achieving decarbonization. And I wonder whether you could use that model, you know, because you were able to calculate the positive benefits of SMRs, could you calculate how valuable it would be to accelerate the deployment of SMRs? In other words, instead of assuming they're only available at 2035, how much should the government spend to make them available in 2030, for example?
So I'm going to hand that over to Dave Sawyer to answer, but I'll say as a sort of a pretext to this, I think this is a fundamentally important question that we're facing here in Canada and would be useful, but globally, I think we have to take a very close look at that. And I say that because even in the Canadian context here, there's a lot of verbiage being given to the idea that nuclear is needed by 2050, but there's a lot of work that has to be done to demonstrate why that is the case and what the benefits are, and we're turning our attention to that. How we can do that, I leave to Dave Sawyer to answer.
Mm-hmm.
Yeah, that's a good question, right? So, and also if you can reduce the costs and increase the breadth of application across end uses. So in the model, we're kicking out annual investments of about, in 2035, about 3 billion in SMRs in the industrial sector. There's a question online, how many units is that? So, you know, this is 19%, roughly 19-20% of total energy for these sectors. And it works out to, I mean, depending 100 to 300 megawatt units, you're sort of 60 to almost 200 units a year. So a pretty heavy deployment. And another question on the thread here was, you know, about regulatory barriers and approval processes.
Mm-hmm.
You know, technology deployment is one thing, but we also have to deal with barriers to deployment, regulatory barriers to deployment while we're doing it. So we can't just focus on innovation. We also have to think about deployment. So that was a good question. But so yeah, so accelerating it, absolutely. You can look at different pathways and say, okay, the costs are lower, the application is broader, Let's put those costs into the model and compete it out. And so that $3 billion investment climbs to sort of $6 billion in 2040. What happens when you shift that forward? What does that mean for cumulative investment? What does that mean for your growth path, your economic growth path, and your emission reductions? Because you're going to get more cumulative reductions probably as well if you can, deploy that technology. So yeah, those are the sort of questions you really need to think about when you're doing your innovation policy.
Mm-hmm. Thank you. So let me go. Let me ask a question directed to you, Eric, and this is related to your study. I mean, and I'm going to go back for a second to this net zero report that the International Energy Agency released last week. So in that report, we have that nuclear energy doubles the global capacity, which is good, but unfortunately, perhaps it's not as ambitious as we would like. And certainly it only includes electricity. And then the report actually relies very heavily on technologies that have very low technology readiness levels. So they are relying a lot on battery storage, carbon capture, utilization and sequestration, what they call this modern bioenergy. So of course, on our side, we are saying, well, nuclear technologies, including small modular reactors, are ready to support this overall net zero. So in this report that you just published a few months ago, the one that you discussed, what are the technology readiness levels for the technologies that you propose, and really what can we do to deploy them in time in order to truly make a dent in this huge challenge that we have with climate change?
Great question. So there's sort of 2 or 3 pieces of the technology portfolio that we talk about. So the deployment model, which is making it in a shipyard and so forth, for example, that's commercial practice today. Large scale commercial practice, hundreds of billions of dollars going into that for the oil and gas sector and for other commercial marine related applications. So there's really nothing complicated there. The process of turning electricity and heat into hydrogen through high temperature electrolysis is earlier stage, but there are multiple companies now announcing factories to make high temperature electrolyzers. So Haldor Topsoe has announced, and 2 or 3 other series has announced in the UK. There are a number of people. That technology basically uses the same technology that high temperature fuel cells use, solid oxide fuel cells. And although those had a lot of reliability issues in the early days, there's been a huge investment in that technology and in the manufacturing approaches and so forth. And there are now, lots of commercial products out there using high temperature fuel cell technology. So we have to adapt that into a system for producing hydrogen, but there's been very detailed engineering studies done at US national labs, designing like all the different pipes and pressure vessels and valves and everything that you would need. And these studies not only kind of demonstrate how practical and achievable these are, but they demonstrate that really the percentage of the cost of that type of system that is related to anything with any technology risk at all is about 10% of the cost. So in other words, it's the large scale manufacturing of the electrolysis membrane component. But very large companies, as I said, have done a lot of work on this. And I mean, you may not know this, but there are over 150,000 solid oxide fuel cells deployed in Japan in people's houses and buildings. And so this is a technology that is I would say at a level where it is ready to go into these types of applications. It's not demonstrated in large scale electrolysis. Apart from that, everything else is stuff you could order from a supplier today. Now, the only part that we need to accelerate the development of is the heat source that is providing the heat for the steam turbines and the electrolysis component. And this is, you know, an advanced reactor. And so we think that, you know, I think John talked about how several of these advanced reactors are making their way through the process in Canada. We have the same kind of process going on in the US. We have several advanced reactors that have been awarded large contracts by the Department of Energy as part of the Advanced Reactor Demonstration Program, and are scheduled to be completing their demonstrations in this decade. So, you know, the issues that need to be resolved here are primarily kind of last step of the commercialization process engineering issues. There aren't a lot of science imponderables. There are not a lot of, you know, materials challenges. The design that we used was based off some other people who are talking about molten salt reactors, and they're talking about replacing the reactor vessel every 4 years. So there's no question that you can make materials that will last long enough for that kind of application and so forth. So, you know, we think that what there needs to be is a real will to say these things could make a tremendous difference. They could be transformative. They could be basically like the other half of our decarbonization strategy could be delivered by this type of technology. And we need to stop thinking that there's some sort of like magic number in the 2030s, which is when these are going to be ready. And we need to figure out how to have people work on them 24 hours a day and accelerate the timelines and get them ready for large scale deployment in the early 2030s. The other piece that is explicitly part of our program here, and why we are publishing on this and why we're publishing on repowering coal and so forth, is that we really need to get these out into the market. We need to both develop the market and the applications, and we need to develop the technology. And viewing it as a sort of, well, let's get the technology developed first, and then, you know, once we get one proven, then, well, build another one. Right? If we think about it like that, they will never be useful in any kind of scalable way. So we need to develop the highest volume applications for these. We need to design what those applications are, get the specifications figured out, the requirements figured out, get them agreed by the kind of stakeholders and investors and other people that would be deploying these, and really show the power of this, and do that at the same time as these things are making it through the last stages of their demonstration programs. So
no, I completely agree. I mean, I think that you alluded to something that actually Kirsty says very often, and I would like to maybe highlight that here. She always says that renewables didn't get cheap magically. I mean, it took a concerted effort from both government and industry and regulators, and obviously there was a lot of work to make sure that, yes, the technology was there, but at the same time, the markets were created, the incentives, whether they were policy or subsidies, were created, and everybody, I mean, and all this created this overall confidence and long-term vision that really was quite important for the global, I mean, for the industry, but also for the financial sector. So I think that you bring a very, very good point. I see that John wants to add to what you just said.
Yes, I want to add to what Eric was saying, but also your comment, Sama. You know, as someone who comes from the renewables space for, you know, the last 20 years or so before coming over to nuclear, it's very frustrating sometimes to hear policymakers and stakeholders who, you know, really believe that renewables are 100% of the answer, and often they are speaking about the cost of nuclear, right? And saying that we have got everything on the table that we need right now with existing technology, and if you're going to invest in these technologies of the future, like small modular reactors, really it's a form of climate action delayism, you know, and that if we just diverted those dollars into into intermittent renewables, you know, these low-cost renewables, we can achieve everything we need to right away. And of course, to your point, Sama, it took 20 years to achieve those sort of cost efficiencies that we hope to achieve through approaches like Eric has outlined, and through the sort of mass production of small modular reactors. But to Eric's point, we have this unhelpful dialogue in Canada that, as I said, we shouldn't be, you know, investing in concurrently in these technologies we need in the future. And Eric's findings around, you know, using renewable electricity to power for fuels and the cost associated with that, I think it was $71 trillion or something like that, compared to what we could achieve, you know, with $17 trillion using nuclear to do the same thing. This is incredibly important information to, you know, fuel these conversations and these debates. And the very last thing I want to say about this is, one of the things that's very helpful about small modular reactors, nuclear being used in heat applications, whether it's hydrogen or other forms of heat, is that it sort of removes us from contentious discussions with renewables around clean electricity, right? So I think it's a very healthy move for us to be doing.
I agree. No, those are very important points. You know, I wanted to maybe go back for a second to something that several of you have mentioned, and actually we have a couple of questions that touch to this. And this is about the ecosystem, everything else that needs to happen in order to make these technologies to actually deployed cost effectively and in a timely manner. So perhaps I was going to start with John, because as I mentioned earlier, clearly in Canada, there are several specific initiatives that are trying to really accelerate a little bit the deployment of SMRs in particular. You know, things like the regulatory alignment and maybe the facilitation of financing frameworks and perhaps policies to create appropriate markets, etc. So do you mind, John, to give us maybe a little bit of a overview of some of the things that are happening in Canada that perhaps could be replicated or you know, adapted to other markets?
Yeah, sure. Thank you for that, Sama. So some of the things that come to mind around the things that the challenges or the things that we have to be mindful of as we try to develop and deploy small modular reactors in Canada. One is we are taking a multi-stream approach. I touched on this in the presentation, but we're taking a multi-stream approach that recognizes Canada's needs, I think. So there's a strong recognition that for small modular reactors to be cost effective, they need to be sort of books of business, or at least a number of units that are built out rather than one-offs. And so in these three streams that we've chosen, we have a discrete pathway for each of them that is intended to result in multiple units being deployed in the Canadian context, and that giving us the sort of foundation that we can use not only to demonstrate cost-effective nuclear in each of those streams, but then to begin to help other nations decarbonize their economies using those technologies. I'm a big proponent of nations, you know, taking a look at how those small modular reactors, the advanced nuclear, can be used in their own economy to achieve that scale of production, because it just makes sense. In Canada, we have a need for certain types of technologies in heavy industry, for example, certain sizes for on-grid applications, and we've got certain strengths for advanced nuclear design, which we're taking advantage of all of those. On the regulatory front, we are working very closely with the US and the UK. In particular, with the US, we've set up a regulatory task force that is not only between the Canadian Nuclear Association and NEI in the United States, but also a formal agreement between the regulator in Canada and the US to try to streamline the regulatory and licensing approval for those technologies. We're keeping an eye on the fuel situation because in Canada, of course, we have been using natural uranium and we're going to have to switch to enriched fuels. That's causing discussions between the US and Canada on how we're going to deal with those issues. And I'll just say on the finance side, because you brought it up, Sama, you know, my experience, even in the renewable side, it took a number of years, a decade, for funding and investment partners to get their head around whether or not it was really safe to invest in solar, for example, right? It takes a lot of work for these institutions and financiers to get their head around a new technology and move away from things that they're comfortable with, be it fossil fuels or other things. So a lot of work that has to be done on that front for sure.
No, that's great. I mean, you know, as I will come back to this because we have several questions about obstacles and challenges. But before we go there, I wanted to go to Eric. You know, your study, you do a couple of, I mean, I know it could probably be applied to essentially any country in the world, but you do some case studies for Japan, the UK, Korea. So is there any particular reason why you chose these countries in particular? I mean, are there specific advantages or technology preconditions that make those markets particularly suitable? And then maybe a follow-up to that, you know, obviously there is a number of newcomer countries out there that currently do not have nuclear energy. Perhaps, you know, this opportunity that produce electricity and heat with nuclear reactors may be a game changer to those countries. So you know, what do you think would need to happen, or what could we do to incorporate this idea into these countries?
Well, fantastic questions. So all three of those countries are highly developed countries with commitments to decarbonization, and Korea and Japan, they all have well-established nuclear industries and have kind of broad industrial capability, which is, you know, manufacturing many of the components in their energy system and so forth. So they all are in various stages of not committing to nuclear energy in any serious way. And so they have a kind of the biggest opportunity and also the biggest kind of missed opportunity potentially here. And we see, for example, if you look at the Korea map, there's absolutely no way that they can build either that solar or offshore wind. You know, it's possible that the UK could take up half the North Sea and, you know, negotiate that with their good friends, but no longer common European common members on the continent. But that does not include the land area required, the sea area required for decarbonizing the electricity sector. So this is just for substituting for fuels. And so we see that there's a kind of opportunity, and that opportunity might even extend to being a large-scale supplier of hydrogen and fuels to other countries. So Japan, Korea, and the UK all have a strong enough nuclear industry and a strong enough industrial capability that if they built the gigafactories or if they built the ships, they could be not only supplying all their own energy needs, but they could become global suppliers to the other countries that may not be as far down the path on nuclear or may have already made kind of unwise decisions about nuclear energy. So I think the second question about how do we get the broader value proposition incorporated, this is one of the areas that we spend quite a lot of time on, and that is both kind of educating people about these systems. So for example, making a flexible plant by using thermal energy storage. Thermal energy storage exists in the solar industry, and nuclear plants exist, but we haven't put the sort of chocolate and the peanut butter together to get a flexible nuclear plant out of that yet. But it's not really a technical, there's no kind of like fundamental science or something that needs to happen to make that. It's more of an application engineering and application deployment thing. So we are doing quite a lot of targeted work to support modelers who are doing decarbonization models to bring the new applications in, to bring a better understanding of what drives the costs, to bring this, so basically sort of like what the Canadians presented here, but much broader across all sectors, and to basically be the you know, to bring that kind of understanding of this broader role of nuclear energy and make sure that it's legitimately incorporated into the modeling tools. And we've done that in the UK, and some very interesting modeling results are going to be published in the next couple of weeks.
Yes. Now, that was going to be one of my conclusions for this. So, I think we are getting to the end of the time that we have reserved for this webinar. So I would like to, before I close, I would like to ask you one last question to all of you, to maybe so you can make some closing remarks with that question. And this is a little bit something that has me very, very concerned. Very recently we saw the UNFCCC synthesis report for all the national determined contributions, and I think you saw something that was quite depressing. Essentially, looking at what we have committed to so far, we will achieve less than 1% of the 43% emissions reductions that we were supposed to achieve. So to me that is quite depressing. So at the same time, we see a lot of these big speeches and a lot of net zero pledges that are coming from many countries and many organizations. So sometimes I worry that people think that we really are doing what it takes to get where we need to get, and in reality we really are not anywhere there. So maybe very quickly from you, what do you think that we need to do? What can we do to really get the necessary action happening beyond all these words? Maybe I'll start with John.
Thank you, Sama. Well, just briefly, I think we have to, this is going to sound counterintuitive because I do spend so much of my time here in Canada working with the renewables groups. But I think in Canada and globally, we have to convince the world that, we really are not going to be able to achieve a net zero future without nuclear. And not just nuclear electricity, but the things that we're talking about in this webinar today for all of its uses. We have to demonstrate that small modular reactors are an enabler of some of the existing technologies that we have, and are going to create more opportunities. So I think we have to demonstrate those two things. And lastly, in the Canadian context, and I'm sure this is true in many other places, we know that we're going to need 2 to 3 times the amount of clean electricity that we have to go through this process of decarbonizing economies. But there's no the political will to talk about that need for doubling or tripling electricity generation really isn't coming through here in Canada, and in most nations. To me, it just seems that the focus is on cleaning up their existing grid, and we need to go much further than that. So those are the things that come to mind for me.
Yeah, thank you. Those very much resonate with me. Dave, did you want to add something?
Yes. So, long-term policy packages sending signals that innovation pays, and that we need to basically invest in these sort of wildcard technologies to solve the decarbonization challenge. I mean, that's really where we need to go now. Like, that's a short-term move. So put in broad-based carbon pricing, broad-based regulations, performance-based regulations that allow choice about how compliance occurs. Innovation programs, governments have to demonstrate they mean it, and then they have to signal that, yeah, carbon's getting more expensive in time. And when we start getting into prices, around $200 a ton, the innovation signal gets really strong. So I always think about EVs and PVs over the last 10 years or so, about the declining costs. And we've had, sort of a global slowdown in 2007. We've had weak carbon policy, lots of electricity policy, but look what innovation's done. So imagine if, innovators really believe these tech are going to be deployed, and then businesses believe they have to switch their capital out during their capital replacement cycles into ultra low emitting technologies like SMRs. So yeah, do you believe the policy is real? And that's a big deal, I think.
Yeah.
Thanks.
No, thank you, Dave. That's very good. So Eric, you have the last word before I close.
Thank you. So I think so I would strongly agree with what has been said already on this topic, but I would add that we need to move from advocacy, from a kind of posture where we think the question is, should we care about climate change or not? Should we sort of be shouting and telling people that something needs to happen? That's kind of that's a cartoon version of advocacy. We need to move from that to really careful planning about how we're going to accomplish these things in the time frame that we have. And once you start doing that, you all of a sudden become very aware of a lot of risks to these different pathways. Even with the good policies that Dave was just talking about, there's still, things are sticky. People, turns out they don't want to get rid of their old heating system or, whatever. There's just stuff that gets in the way. Reality bites back when you start to try to do stuff. And we do not have any plans anywhere. I have not seen a single country's decarbonization plan that could even be called a plan in any kind of legitimate context. So we need to move from we have a target, we're feeling good because we've committed to something, whatever, to this is how we're actually going to do these things. And when we do that, and when we start confronting these risks, the kinds of things that Dave and John were talking about will become really, really valuable because they don't, you can have multiple pathways that don't all have the same risk. If your risks if you have a huge amount of risks around behavior change, be really nice to have some pathways that work even without behavior change, for example, right? So we need to start really thinking like this. And when you do that, when you really put yourself in the present and say, what am I going to do tomorrow? What am I going to do the day after? And stop kind of thinking about, so yeah, we got to 2050 and somehow magically it all worked. Then you start thinking like somebody who's actually planning for their retirement and wants to actually have money when they retire. And so they actually care about, well, I'm not just going to put it all in Tesla because it looks like it's going up now, but it could go down just as easily, right? And so then you have a broader strategy and you're more likely to succeed at your goal. And this, I feel like this is something that we need to start advocating for, is actually this kind of risk-informed actual planning of how we're going to get there. We have such a short amount of time. We almost don't have time for doing it and making a mistake and then redoing it.
Exactly.
We've got to kind of figure it out. Yeah.
No, I would agree. I mean, I would agree with everything that you all have said. I mean, the importance of having a long-term plan, provide signals that would incentivize the right behaviors. That's very important. I would agree the importance of going beyond. I mean, probably in developed countries, it is okay if we focus a little bit on cleaning our current act, but particularly if we look at less developed countries, that's not enough. I mean, their growth is going to be enormous, both in population and in energy needs, if we want them to achieve the standard of living that we have in Canada or the US or the UK. So those things are super important. And finally, I completely agree with all of you that we need to move from grand speeches and scenarios to actually well laid out plans where we assess all the risks and see how we are going to actually overcome them. So in that sense, I will close, but just maybe advance to all the people that are here, that from World Nuclear Association, we will continue working in this area. Certainly the area of the role that nuclear has in sectors beyond electricity is something that we are going to continue bringing to you. And as Eric anticipated, there is a number of reports that are coming up that will illustrate this very, very clearly. But in general, I think that one of the big things that what we need to do is make sure that we have a clear set of scenarios where this important role is clearly laid out. So organizations such as the IPCC or the International Energy Agency or others can actually have a roadmap to use the very clear potential of nuclear energy, both for electricity and other non-electric sectors. So we'll continue with that. And then obviously we continue to work in other areas such as innovation and everything else that we need to do to make sure that the important role that nuclear has towards addressing climate change and energy security is going to be clear and actionable for our policymakers and the financial community. So I will leave you here. I know we've gone a little bit over time, but hopefully it was worth your while. And please look at the World Nuclear Association website, because this webinar will be posted there in a few days. And please keep an eye on other activities, because many other exciting webinars and initiatives and reports are coming out that hopefully are going to help us moving forward the role of nuclear in this important crossroads that we find ourselves as the human race. So thank you, everybody. Have a very good rest of your days or good evenings. Thank you very much, Eric, Dave, John. I truly appreciate the time that you have spent explaining these very important reports that you have prepared for us. Thank you so much.
Thank you.
Bye-bye, everybody.